Objectives. Find Taylor and Maclaurin polynomials. Form Taylor and Maclaurin series. And find the radius and intervals of convergence of a series. Are we starting? Alright. Today we're learning Taylor and Maclaurin series. Let's start with the Taylor polynomial.
Technical difficulties?
So, we have f of c plus f prime of c times x minus c over the first factorial, then the second derivative f of c plus x minus c to the second power over the second factorial, and then it keeps going until it's just, f of n times f of n of c. This is the general Taylor polynomial. So, now let's work with it. We're going to do f of x equals 1 over x about c equals 1. So, f of x, equals, I remember that. F prime of x negative 1 over x squared, x double prime of x equals negative 2. I'm sorry, that's not negative. Because remember, when you do the derivative and you bring the x squared up, it becomes x to the negative 2. X to the negative 2 times the negative 1 equals positive 2. So that was not negative. So now we have 2 over x to the third, f 3, remember you have to write everything out. It's negative 6 over x to the fourth, negative 24 over x to the fifth, it's about 1, so we have to do f of 1 is just 1, f prime of 1 is negative 1, f double prime of 1 is 2, and we continue this. So here we have our Taylor polynomial. We're not done. We need to write it in our format. So our P5 of x comes out to be 1 minus x minus 1. It comes out as 1 plus a 2 x minus 1 to the second over 2 factorial minus 6 x minus 1 cubed over 3 factorial plus 24 x minus 1 to the fourth over 4 factorial minus 120 x minus 1 to the fifth over 5 factorial. Now, do you notice a pattern with these numbers? Can we say that 2 times 1 equals 2, and 2 over 2 cancels out? How about 3 times 2 times 1? Isn't that just 6? If this becomes a 6, these will cancel out. 4 times 3 times 2 times 1 is just 24. 24, and those cancel out. 5 factorial, you guessed it, is 120. So that equals 120. Then these end up canceling, and now you're only left with this formula. So now let's rewrite it. So after we cancel out all that we have, we're left with b equals 1 minus x plus minus 1 plus 2. Actually, we canceled out those 2's, so they are irrelevant. So now we're just left with x minus 1 squared minus x minus 1 cubed plus x minus 1 to the fourth minus x minus 1 to the fifth. And there you have it. That is the Taylor polynomial for 1 over x. Well, hello there. Now we'll be working on Maclaurin polynomials, which are so much easier than Taylor polynomials. That's because they're centered on 0, and that's just a lot easier. 0 is just always easier.
Always.
So, let's start with one of them. Pause for dramatic effect while I go look at what we're doing. Alright, so here's an interesting one. Let's try f of x equals ln of x. So as we start doing this, we can see that, alright, f of 0, ln of 0 does not exist. It's undefined. So, we can't use this. We've got to do something. We've got to say, it's not just f of x, but we've got to add this 1 in here. So let's say ln of x plus 1. That makes it a whole lot easier to just say, alright, f of 0, we plug 0 into this formula, 0 plus 1 is 1. ln of 1 is 0. You should know that by heart. So, we can continue. I'm going to elevate down here. Alright, so now we have, where did it start? Alright, so we got f of x, ln of x, and we plugged in the 0 for f of 0. And we ended up with 0, 1, negative 1, 2, and negative 6. So our polynomial is going to say 0 plus x minus x squared plus 2, 3 over 3 factorial minus 6 over 4. Alright, so now we have 0 plus x to the second over 2 factorial plus 2x to the third over 3 factorial minus 6x to the fourth over 4 factorial. We can simplify that and say x equals x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4. Ta-da! So now we know that a Maclaurin series of f of x to the ln of x is x minus 1/2 of x squared plus 1/3 of x cubed minus 1/4 of x to the 4th. And we can use these polynomials in order to approximate numbers. So if we wanted to approximate, hold on, let me set this up again. Alright, this is the Maclaurin polynomial to fx equals ln of x that we just found. So if we wanted to approximate something, so let's say ln of 1.2. Well, remember what we did at the beginning. We made ln of x equal ln of x plus 1. So this polynomial is actually x minus 1. So when we plug in the 1.2 as our x, it should be 1.2 minus 1, which is just 0.2. So we plug in the 0.2 into where the x's are. And we have 0.2, 0.2 here, 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 everywhere. So, plug this into your calculator, and I already did the calculation, so, and I got, go down here, I got this as P of 4 of 0.2. Now, if we try doing ln of 1.2, plug in of ln of 1.2, and you get this number. Alright, the 0, 1, 8, 2 matches up. So our approximation is only accurate for 3 decimal points. Alright, our next Maclaurin polynomial will be f of x equals e of x. Oh. Now, if you know your derivatives, you know that f of x equals e of x, f prime of x equals, oh wait, e of x, and double prime of x, also e of x. So, and it just continues like that. So, if you plug in f0, e to the 0 is 1. F prime of 0, also 1. F double prime of 0, 1. So, now that we got that, and we know it continues exactly on that path, we can just start the Maclaurin polynomial. I'm just going to leave this open, because we can keep going after we keep writing. Our first one, 1. X times 1 is x, plus 1 times x squared over the second factorial, or 2 factorial, sorry. And we can actually keep going because we can see this pattern continue. We know the next one's 1. We can say, oops, that was supposed to be 2. X to the third over 3 factorial. Continue on. X to the fourth over 4 factorial. And it just keeps going. So, the Maclaurin polynomial of e to the x is pretty simple. If we wanted to do an approximation for e to the x, we wanted to say, what's e to the 0.5? We can plug this into our Maclaurin polynomial and say, alright, p is 0.5 equals 1 plus 0.5 plus 0.5 squared over 2 factorial plus 0.5 3 factorial cubed we plug this into our calculator and we get this whole thing is going to equal 1.648. That's an 8. By the way, that's an 8. So when we plug in our P of 1.5 into E of 1.5, we ended up with 1.648719618. Now we plug in e to the 0.5, my bad. And we end up with 1.648721271. Alright, so we can see that it's all the same up to the 7. So our Maclaurin polynomial is only accurate for 5 significant figures. And that is how you do e to the x and approximate it. Alright, this is the formation of a Taylor series. As you can tell, it's almost exactly the same as a polynomial. Taylor polynomial. This is the formation of a Taylor series. As you can tell, it is in the same format as a Taylor polynomial. So let's use it with a Taylor polynomial. We're going to use the series I found already, the 1 over f of x equals 1 over x, about x equals 1. And we're going to use that to make a Taylor series. When we do this, we have to look at it. Alright, so from n equals 0 to infinity. So, as we do this, we notice that it alternates from positive, negative, positive, negative. So, only way to put that into the formula is we say negative 1 to the n. That way, we can see that it changes. So if we were to plug 0 into, for n, then negative 1 to the 0 is 1. That's positive. We go on, n equals 1 now. We plug in n for 1, negative 1 to the 1 is a negative, so it continues. So negative 1 to the second power is positive, so it just continues like that. Now we look at the formation. We can tell that it's going x minus 1 to the first, or first it doesn't exist, then it's x minus 1 to the first, then it's x minus 1 to the second, so you can call it safe to say that it's x minus 1 to the n. Since if n was to equal 0, we would say x minus 1 to the 0 is just 1. That's why it's not on the first term. And then if we were to say n equals 1, it's the first x minus 1 to the first power, x minus 1 to the second power, and then so on. So this is your Taylor series for f of x equals 1 over x. So now we're doing the Maclaurin series for fx equals ln of x, which we've already done, and we know that it looks like this. So if we were to put in the Maclaurin series, we would write it as, and you see that it's x minus 1, so we can't start at n equals 0. We have to start at n equals 1, or else it gets mixed up, which makes sense, because if you plugged in a 0 into ln of x, it would be undefined. So it makes sense that you have to start at 1. So you put to infinity, because it just keeps going, and so we see the pattern it goes in, and we can already tell that, okay, so the x pattern continues with the exponents increasing by 1, then by 2, and then by 3. So we can say that this is x to the n over, and then it also increases over 1, over 2, over 3, so x to the n over n. Now that we have this, we can find the interval and radiance of convergence of this series by using the ratio test. So, the ratio test is limit as n approaches infinity of an plus 1 over an. by looking at this, we can say an plus 1 equals, so we add the plus 1 to the end, so x n plus 1 over x plus 1. And our a to the n is obviously just going to be what we have here, which is x to the n over n. So now we have the limit as n approaches infinity of an plus 1, which we said was x plus 1 over, or x to the n plus 1 over x plus 1 over our series ratio. Alright, so putting it into the ratio test, it shows as a limit as n approaches infinity of x to the n plus 1 over n plus 1 over the x to the n over n. So that would be our a n plus 1 over a n. So, and doing this out, we can say, we multiply these out, and it shows that n, so x n plus 1 over n, or, yeah, n plus 1 to the x of n. So we see that, alright, so we see that this is x n plus 1. And we know that when you multiply exponents together, it's an exponent plus the exponent. We're just doing the opposite here. So if this is an exponent plus an exponent, we can separate them and say x to the n times x to the first power over n plus 1 x to the n. Now we see that these cancel out, and we're left with the limit as n approaches infinity of n x over n plus 1. And don't forget those absolute values. Those are very important. Now that we have this, we can test the convergence by making it less than 1. So the first thing we can do is say, take out this x and put it on the outside of the limit. Say x, limit, n approaches as n approaches infinity. And what we can also do is take out the n. And when we do that, this n becomes, the top n becomes 1. And this n right here becomes 1 plus a 1 over n, because that n was taken out. And we can see that as the limit as n approaches infinity, when you plug n in here, 1 over infinity is 0. So this just ends up being 1 over 1. So what we're really looking at here is x is less than 1. Oh, sorry. So, okay, absolute value of x less than 1. So, absolute value of x less than 1 also says that negative 1 of x less than x less than 1. And this is our interval of convergence. We also need to find out if these are convergent or divergent, so we know if to include them or not. So now that we found our intervals, we can test them. So now we plug in negative 1 into our original equation. Negative 1 to the nth power over n. So we see that we have a negative 1 to the n, which is an alternating sequence. So we need to do the alternating series test. An alternating series test says limit as n approaches infinity to, so we're going to put in 1 over n, and at the limit as n approaches infinity, would be 1 over infinity, which equals 0. According to the alternate series test, if the limit of n approaches 0 and it's decreasing, and we can tell that it is because as we plug in more points into n, we see that this series is decreasing. The limit as n approaches infinity is 0, and it is decreasing. So yes, it is convergence. So up here, we know that it's included. So now we test 1. So now we're going to do f of 1 1 to the n over n. 1 to the n is just 1. And if we have this right here, 1 over n. 1 over n is a harmonic series, and harmonic series are always divergent. So we know that this is divergent, meaning this is not included. So this is our interval convergence for this series.